Hi, so now we are tackling just one section in the textbook, 14.6 in the textbook, but it covers a lot of topics from the College Board. So we are going to start talking about reaction mechanisms. And when we talk about reaction mechanisms, we have to talk about elementary reactions. So we're going to cover 5.4 and 5.7. And then we're going to incorporate rate law into these. Before we talked about you need experimental data to determine a rate law, and now we're going to counteract or contradict what we said earlier. No, actually you can just look at a reaction, look at a balanced chemical equation and figure out the rate law. And we'll look at multi-step mechanisms. So let's first start just by talking about what a mechanism is. So when we think of a balanced chemical equation, you look at reactants and you look at products, and there's nothing about what goes on in between. And the reaction that I like to highlight for this is the photosynthesis reaction. 6 carbon dioxide molecules and 6 water molecules react to form 1 glucose and 6 oxygen molecules. That's photosynthesis. And it's the reactants, and those are the products. I think even in freshman biology, but especially if you took AP biology, you know this is a gross oversimplification of that process. Do you really think that 12 molecules collide at exactly the same time with exactly the right orientation? Of course not. This is a series of many, many, many individual collisions. You may remember back, it's the first set of collisions we call the Calvin cycle, then there's photosystem 2, then there's photosystem 1. I mean, this is a very complex process. So this might be a balanced chemical equation. This is certainly not the reaction mechanism. Each one of the individual steps of a reaction mechanism is called an elementary step or an elementary process. That exists or that describes just one collision. So it may have 1 or 2 reactant molecules, rarely 3, because it's just one set of collisions. So if we look at this chemical equation that we've used a few times, nitrogen dioxide plus carbon monoxide yields nitrogen oxide plus carbon dioxide. Seems sort of simple, and oxygen gets transferred over. But this does not happen as one collision. The first thing that happens is that 2 nitrogen dioxide molecules have to collide. When they collide, we make NO3 and NO. NO happens to be one of the products, but the NO3 goes on, continues to react. That's what collides with the carbon monoxide to produce a nitrogen dioxide molecule and a carbon dioxide molecule. If you look at this, you can see how it does add up to be that overall reaction. One of the nitrogen dioxide molecules that's consumed in the first step is reproduced in the second step. So it's very similar to like adding mathematical equations, where if it's on the reactant side and the product side, you can cancel it out. And the same thing is going to happen to NO3. NO3 is produced in the first step and it is consumed in the second step. So it is not a reactant and it's not considered a product. What it is considered is an intermediate. An intermediate is a substance formed in one elementary step of a multi-step mechanism. It's consumed in a subsequent step. So it's formed and then consumed. So it's not considered a reactant nor a product. It's sort of its own thing. It's an intermediate. And you will see these reaction profiles will look a little different because the first part is the first reaction. In this case, maybe making that NO3 and NO. And then the second piece of this is that second step. And so each one of these have their own activation energy, They have the delta E, the change of the reaction, is still just the difference between the reactants and the product. So if we were looking at what is the change in energy of this reaction, we don't worry about the transition states or the intermediates. It's always just products minus reactants. So let's take a look at an example here. It has been proposed that the conversion of ozone to oxygen gas proceeds by a two-step mechanism. Describe the molecularity of each elementary reaction in this mechanism. Molecularity, if you cheat and go on to the next page and you look at this graphic, the molecularity is just a fancy way of describing how many molecules or how many species are reacting. And so if we look at this first reaction, you see that it's just O3 decomposing. So this is unimolecular. The second reaction shows two species colliding. So this would be bimolecular. Part B says write the equation for the overall reaction. So if I look, this is what I'm doing is I'm looking what can cross out. I make oxygen as a product in the first reaction and use it as a reactant in a second reaction. That's what I can cross out. So now I just add up all of the reactants and all of the products. So one ozone plus another ozone is two O3 molecules, two ozone molecules. And then in the first reaction, one oxygen molecule is formed. In the second reaction, two is formed for a total of 3 oxygen molecules. If I look, it's obviously going to still be balanced, 6 oxygen atoms on both sides. And the intermediate was this oxygen atom. And when we talked about ions and forming compounds back in first year chemistry, we said oxygen was a diatomic element, meaning that it never exists in nature as just one atom by itself. The reason why that is because it's so super reactive. And now you can see that, yes, this isn't just an oxygen atom floating around. As soon as that oxygen atom is made, it gets used up again. So this is the part where what we discussed at the beginning of the chapter is not necessarily technically true. And that is, can you write a rate law just by looking at the chemical equation? Well, it depends. It depends on if the chemical equation, if we know that that is an elementary step. If that is a single set of collisions, then yes, I can predict what the rate law will be based on that. So it's always going to be just basically the coefficients become the exponents. If I know, and this is only if I know, that it is an elementary step. So if I think about this reaction right here, right, it would be 2A molecules. So the exponent on A is 2, right? Here it would be 3A molecules. So the exponent on A is 3, and so on. We can look at the rate law, coefficients become exponents. This is only true if we know it's an elementary step. So practice exercise 1 says, consider the following reaction. 2A plus B yields X plus 2Y. You are told the first step in the mechanism of the reaction has the following rate law. Which of the following could be the first step? And Z is an intermediate. So if this is the rate law, then, it tells me that this is the first step, so this is an elementary step, I know that it must be just A plus B. And the only one that is A plus B is answer choice E. Practice exercise 2 says, consider the following reaction. Write the rate law for this reaction, assuming it involves a single elementary reaction. If we know it's a single elementary reaction, then it's just coefficients become exponents. Rate equals K times the concentration of NO squared times the concentration of Br2. And B says, do you think this is likely, that this is a single step mechanism? And not really. It's not right. It's not likely. The reason why is this would mean 3 molecules colliding at exactly the same time at exactly the right orientation. It's not impossible, but it is very rare. So if you see a rate law looking like that, chances are that is a multi-step mechanism, just because 3 atoms colliding is so rare, or 3 molecules colliding is so rare. So if I have a multi-step mechanism, what determines the rate law? Because it's not just going to be maybe 1 and then 2 and then 3 reaction mechanisms. And this is the big concept here, that the slow step is the rate determining step. This is in any process, right? No matter how fast an assembly line works, it doesn't matter. The only thing that matters is how fast the slowest step goes, because that's going to limit the amount or the rate at which the reaction or the assembly takes place. So this is the decomposition of dinitrogen monoxide, believed to be this. Notice that it tells you that the first step is slow. The reactions, they're going to tell you that the first step is slow. So write the equation for the overall reaction. So this is where I look at reactants and products. What can I cross off? I think I can cross off the oxygen atom. And that's the only thing that I can cross off. So the overall equation is 2 nitrogen dioxide. That's the only reactant decomposing for 2 nitrogen gas molecules plus an oxygen gas molecule. And then double check, make sure it's still balanced, right? If you messed something up, it may not be balanced. Write the rate law for the overall reaction. So this is pretty easy because I know the slow step is the rate determining step. So now I can do just like I did on the last example, rate equals K times the concentration of N2O, right? This is the only reaction I'm worried about. The coefficient becomes the exponent. What is the intermediate in this reaction? Well, it's actually the same intermediate, that oxygen atom. The oxygen atom is the intermediate because it is consumed in the first step and used in the second step.